So hello everybody and welcome to another fun-filled episode of Tin Time. This is just going to be a quick one. What I wanted to do is I was kind of working on an oscillator circuit from back when I was working on the Heath kit. So I'm pointing to over there, I know you can't see it, but the Heath kit, that 610, that scope. And it kind of got me thinking about oscillator circuits, a simple phase shift oscillator circuit. And like phase shift, just it's capacitor and resistor, capacitor, resistor, capacitor, resistor. A couple different stages of that, and there's a little more math to it than that, but the simplest ones that I'm finding on the internet to build are just 3 stages, and they use you can either use an op amp, or the one that I chose to build. I'm going to show you the website and everything in a minute, but the one is a 2N222 transistor. I don't know why I just chose that, because that's what I chose, but I'll show you that. But it stems back to the olden days, back when I first started to teach myself electronics, back before the invention of electricity, a long time ago. And whenever they would talk about oscillators, they would always kind of show you that you'd charge a capacitor and it would discharge through the inductor and then charge back up and discharge. But I always wondered where that charge was coming from, and I always kind of in my mind had the idea that there had to be something almost external charging that at the beginning. And well, what I came across here is the fact that it basically charges from the noise when you first turn on the transistor. It charges the capacitors, and that noise is kind of the static, or whatever you want to call it, that charges everything. But when it comes out the other side of the RC network, it's a little bit out of phase, and the initial burst of noise basically comes out of phase and then feeds itself back in 180 degrees out of phase. It boosts that initial burst of noise, and that happens over and over again, and the amount of, or the frequency that you get rather, has to do directly with the delay or the phase shift from the RC network. So there's no external anything. You're merely just feeding the voltage in, and as soon as you do, you get you feed a DC voltage in, and as soon as you do, basically the noise that it created when you first fed it in starts a chain, and the chain feeds itself. So anyhow, I'll show you, but just a quick video on this and building one of these. And there's really nothing to it, especially with the internet. You can look at the internet and get the schematic. You don't even really have to think about it. So let me just get you over and I'll show you that. Alright, so here we are in the website. The URL is deepblueembedded.com/RC shift or phase shift oscillator, and then you can see it right here. You have to bear with me because I think my computer's in the middle of trying to do something, so it's taken forever to there you go, the lag time getting to some things. I think it's just in the mood of where it wants to be rebuilt. So if you look at the formula basically for figuring out the resonant frequency of this circuit, it's right here. So it would tell you that, well, the 2 pi is going to be a constant, and the square root of 6, in this case it's square root of 2 times the number of stages. This has 3 stages, so it's 2 times 3 is 6, and it's the square root of that. So this will also remain constant. These 2 are the only variables that we could have, and since it's the inverse of it, meaning it's not just this times this times this, it's all this, but it's underneath the 1. So it's basically a division problem. Anytime these numbers increase, this number here, the FR, is going to decrease. So if I take resistance up or capacitance up, frequency is going to come down. Whereas if this one wasn't here and it was a straight across multiplication problem, basic math there, anytime these would increase, and so would frequency, but that's not the case here. So anyhow, these through the constants. The only thing I can change is the resistance and capacitance, so I will change the capacitance and we'll see what happens. But I'll show you the circuit that I built, and here it is right here, and here's the NPN, and that's a not P and N. The little arrows pointing out or not pointing in, whatever you want to call it, because the PNP was calling peeing in the pot, but this is not pointing in, NPN. So that means you have to have a positive voltage here on the base to turn this thing on. So here basically there's a design, 18 volts in, and then this is the biasing circuit. There's a voltage divider right here for the biasing circuit. Here is the cathode resistor, and I'm not really sure why they put this on here. Such a big capacitor there, but anyhow, I put it in there as well. 22 microfarad. My computer, as you can see, is starting to think again. And then up here would be this would be the collector resistor right here, and that would set the collector voltage on here. But basically what I want to say, the voltage divider right here, that's just to get the transistor to a point where it's turning it on, and I forget what the voltage is, but it's kind of, for this particular application, it doesn't much matter. We just know it's turned on, and it's going to be operating, and I would imagine on all the time. So what's that, Class A? Is that what that was? It's been a long time. I'll have to look that up. But anyhow, this was a circuit I built, and here they're using 1 nanofarad capacitor with a 10 kilohertz, 10 kilo ohm resistor network. Like here's the first one, and then here's the second one, and then here's, I don't think I can draw on it, but, and then here's the third combination. So I'll show you that circuit now that I put together. It doesn't really look anything like it when you see it down on the breadboard, but I'll show you what it's doing. Alrighty, so there's the circuit. Yeah, that was Class A. I was thinking, you know, the Class A amplifier, it's on for the entire cycle. But let's see if you can see everything. These are the, I have to look. Yeah, here's your three networks: capacitor resistor, capacitor resistor, capacitor resistor. There's that big power supply cap that they wanted, and then there's your biasing and your emitter and collector resistors right there. So it's pretty easy, as you see. And I think if I built one with, I have an op amp here that I could probably use too. It might be even simpler. But I have 18 volts running into it from the DC power supply, and that's right here. My scope lead is on where they showed it before, right from the collector. I think, no, wherever they showed it now. So yeah, it was right at the collector circuit. And let's see what else I have. That's about it. I mean, as you can see, it's pretty simple. So I'll show you the, I'm going to pull this out, and then I'm going to show you the waveform as soon as I get this back in. Let me reposition. Maybe I don't know if I can get both in the same shot. Alright, I'm going to try and I think I pretty much have them both in. Here was where the positive lead's going to go, and you can see the scope. I think you can see, yeah. So you'll see as soon as I plug this in, look, I get a nice DC sine wave. DC sine wave, geez. I get a nice sine wave with just a DC signal into it. Nothing else needed, basically. Just part of the power supply. It produces its own, and that's a little bit over. It's about 6.09, so about 6.1 kilohertz. And if you look at the formula, I think it comes out that with that equipment, or with the pieces I put in there, it should have been about 6.5 kilohertz. So You know, remember, those aren't precision. Those are basically, I just pulled them out of the holes and they're out of the box and stuck them in there. So I'm sure if you recalculate everything, you'd find out it would be awful close to that 6.1. So I think that's totally acceptable. So what I'm going to do real quick is I'm going to take out the 1 nanofarad. Let's see, and what was I going to put in here? Let's see. I have 100 picofarad. So let's see. How about, what did we want to do? We wanted to go down so the frequency will go up. So yeah, we'll put in, would that be 100 picofarad would be 0.1 nanofarad. So we'll go up a little bit and see what happens. So let me just get those swapped out real quick. I'm just going to be changing these 3 caps, and we'll come right back and see what happens to our frequency, or if it even still works, or maybe we change the mathematic formula that much that it no longer is in an area where it oscillates. So give me a minute here.